This is a presentation for Applied Math 105 titled Orthogonality Uncovered. It's an intuitive look at the orthogonality assumption that we invoke often in Applied Math 105. The motivation for this was when you're doing Fourier expansions and diffusion, advection, and Green's function, we often invoke orthogonality arguments to determine the general solutions. While mechanically it's not too difficult to find these solutions, intuitively sometimes there's a bit lacking, and I think that it's a great takeaway from this course to not only know the mechanics, but probably more importantly the intuition behind what we're doing. So a quick example, orthogonality in the real world. I like to think of orthogonality by replacing it with the word independent. So that means that if things are orthogonal, if you change an aspect of one element that's orthogonal to another, that change won't affect anything else in the system. So for example, your computer monitor has orthogonal controls. It has a brightness setting, a contrast setting, and a color balance setting. Now could you imagine how difficult it would be to find a screen setting that would fit your given environment if those things weren't independent? So for example, I have this photo on the left of a group of puppies, and I used the formulation at the bottom of your screen to simulate interdependence of the three toggles: contrast, color balance, and brightness. I made the weights A, B, C, D, E, and F such that it'd be annoying enough to try to get anything reasonable to happen, and by making those numbers high enough, a slight raise in the contrast level prescribed the photo on the right, which adjusted brightness and color balance as well. So basically the takeaway from this is orthogonally is extremely useful because it allows you to make pinpoint and more precise changes to the system in order to fit whatever the functional space you need. So the way we're used to seeing orthogonality is typically in a more mathematical or geometric sense. So to the right we have a picture of a 3D space with orthogonal planes T, G, and A. Now, one thing that you might remember from linear algebra, if you take one vector from each of these planes, you were able to add them together with the appropriate scalars to precisely and 100% accurately describe every single point in the 3 space. And that's a pretty important thing to take away, is that you can use 3 vectors to describe every single point in the given space. So let's assume that we have the basis 1, 0, 0, 0, 1, 0, 0, 0, 1 as defined in E sub A, E sub G, and E sub T. We note that if you multiply any E sub I times E sub J where I does not equal J, the result is 0, which is a defining property of orthogonality, which we'll revisit in the next slide. So a more formal explanation of orthogonality, we note that two non-zero functions g of x, h of x are orthogonal if the integral of their multiplication equals 0. Going on from there, an orthogonal set is defined of any h sub I, h sub j of x dx. That integration is 0 for all I does not equal j and is greater than 0 for all I equals j. But you're probably more interested in knowing how this orthogonality maps to trig functions. So we show you that the set of cosines is in fact an orthogonal set. So first we invoke the formulation above, multiplying cosine of n pi x times cosine n m pi x, both of them over L, and we integrate. And using a trig identity, we can and the fact that it's an even function, we simplify it to get to the relevant cases below. The 3 relevant cases are n equals m equals 0, n equals m does not equal 0, and n does not equal m. So for case 1, when n equals m equals 0, we trivially note that the cosines both fall out as 1s, and you're left with the integral from 0 to L of 2 dx, which equals 2L. For case 2, we note n equals m does not equal 0, and in this case, using another trig identity in the trig, which is located in the trig reminders, we see that cosine squared of x equals the quantity 1 plus cosine 2x over 2, and we also know that sine of 2n pi for any integer n equals 0. We can simplify case 2 into case 2 equaling L. On the next slide, we explore case 3, which is n does not equal m. This is a bit messier, and it's probably easier for just to pause the video if you want to go through the proof formulation. But when n does not equal m, terms fall out and we invoke more trigonometric identities, and when n does not equal m, the integral falls to 0. Therefore, we have shown that that cosines are in fact an orthogonal set, and you can look at Paul's online math notes on Google, or even Bing, I suppose, if you want a more in-depth proof of cosine, or if you want to see the proof of sine. So great, what does that all mean? We know that orthogonality holds for the set of all cosines of different periods. We know that with orthogonal sets, we can use scalars and addition and subtraction in order to describe every space in a given, every state in a given space. So let's put the two together. And Fourier does just that. So we're all pretty familiar with the Taylor series, which uses polynomial expansions to approximate functions. Well, Fourier series is pretty similar to that, except for instead of using different powers, it uses, in our case, different periods of cosine functions in order to express any function. So we write Fourier cosine series as f of x equals the infinite sum from m equals 0 to infinity of b sub m cosine of m pi x over L. And this should come as no surprise, because you already know that cosine is, or the sum of all cosines rather, form an orthogonal set with some scalar, which we denote b of m, required in order to approximate, and in this case, if it's an infinite sum, get exactly f of x. So now the question is, how do we find the scalars? And that's basically just algebra. And again, there's a lot of algebra here, so if you would like to pause the video to get a better sense of what's going on, it might be helpful. The three key takeaways here is we start with f of x equals this infinite sum b sum of cosine of m pi x over L, as we saw in the previous slide. And we multiply that by some cosine n pi x over L. And we already kind of done a lot of the work by in our cosine proof. And so with case 1, we know that the right-hand side integral falls to 2L. By case 2, where n equals m, we know that the right-hand side integral equals L. And by case 3, if n does not equal m, which basically makes a ton of combinations fall out for finite integrals, and in this case, there's always going to be an infinite number of terms in an infinite sum. But that right-hand side integral in case 3 falls to 0. So by rearranging and reordering terms, we actually could solve for the coefficient b sub m. And it has two different formulations. For m equals 0, we are left with 1 over 2L, the integral from negative L to L of f of x dx. And for m does not equal 0, we're left with 1 over L, integral of L to negative L, f of x cosine m pi x over L. And I was also, just a notational frequently asked question, we often write b sub m as this kind of scalar multiplication or dot product of f of x cosine divided by effectively cosine squared. And that's really just, that comes directly from equation, I guess, 3 right here, where we've pulled out this b of m, and we can just divide the right-hand side integral to the left, and it yields this exact same result. So concluding remarks, hopefully that's given you some additional intuition on orthogonality. At its heart, it's a tool to generate linear combinations to describe a function. Eigenfunctions, trigonometric functions, and other sets of mutually perpendicular vectors allow us to use this nifty trick. And so below, I've shown you a few examples of a Fourier series approximating square wave, sawtooth wave, triangle wave, and a semicircle. And the reason it's approximation, well, for two reasons. The first is that it's a finite Fourier series, and in our case, we need an infinite series to get exactly. And then also we note Gibbs phenomenon, which you may or may not have already covered. But at jump discontinuities, you'll note an overreaction of the function. So that's all I got for you, and happy studying.